Okay, welcome to the last part of topic number 6, and this is where we tie together all the things we've learned about maximums and minimums and x-intercepts and y-intercepts and points of inflection, and we learn how to actually put all of these things into drawing an accurate representation of the graph. The 6 steps are listed here, 5 steps are listed on page 14. Step number 1, find the x-intercepts of your function. And of course, you do that by setting your y equal to 0. Step number 2 is a very simple step. Find the y-intercepts by setting x equal to 0. You know the other coordinates are going to be 0 there as well. Step number 3, find your critical points. Now that would mean taking the first derivative, setting it equal to 0. That will give you your critical values, your maxes or your mins. Don't forget, you need the y values as well for that because these are points. You also want to find the point of inflection, if there is one. And so what you should do there is take your second derivative and set that equal to 0. Okay, step number 4 says, once you know what your critical values are from here, your critical points, x values, use the second derivative test to determine the nature of the point. So in other words, are they maximums or are they minimums? Okay, so we need to do that. And step number 5 says to use the second derivative test to determine concavity. Now that's what we did in the last lesson. That's going to require the use of a table. All right, and that concavity test is used as a check to make sure that those critical points are behaving like they're supposed to. It's just a check because sometimes what you think is happening is not really what's happening. Okay, so here we go. Step number 1. Again, this is on page 14. Let's get the x-intercepts first. All right, so the way I get the x-intercept is I set y equal to 0. And so I'm actually solving the equation. 0 equals 6x minus x squared. And you have to solve that however you know how to solve that. Fortunately, this one factors. It has a common factor of x, and then will be in front of 6 subtract x. And because it's equal to 0, we can use our zero product property now. This piece tells you that one solution is x equals 0. This piece tells you one solution is x is equal to 6. And now because they're x-intercepts, you know what the y coordinates are going to be. It's going to be 0. So your x-intercepts are 0, 0, and the other one is at 6, 0. They're going to be your x-intercepts. Now if you wanted to, you could actually plot those on that piece of graph paper there now, or you could save it all and do it at the very final step. So 0, 0 is about there, and let me see, the numbers are very small, but 6, 0 I'm thinking is about right there. So there's your two x-intercepts. Step number 2, you have to get the y-intercept. Okay, well what you do there is you set your x equal to 0. In fact, if you look carefully, you can see that we've already got the y-intercept right there in the origin, but let's just do the workings anyway. So y is going to equal 6 multiplied by 0, subtract 0 squared, and of course that's going to give you 0. So the x coordinate must be 0 because it's a y-intercept, and the y coordinate is also 0. But like I say, that's already the point that you plotted right there. Okay? So that's the first two found, the x-intercepts and the y-intercepts. Now I'm going to have to erase all this so that I can go back and now give some room for my next calculation. All right, so my next calculation is going to have to be find the critical values. Like what are the maximums, what are the minimums, so we'll just work those out. But I don't think there's a quick way to erase all this. I don't think there is. Okay, so let's go back now. Step number 3, let's find the derivative, y prime, and that's going to be 6 minus 2x. And of course we set that equal to 0. We set that equal to 0. We're going to get 6 minus 2x equals 0. So 6 equals 2x. And of course you divide both sides by 2, and you get x is equal to 3. Okay? Now remember, you're going to need the y value there as well. So if you plug that x back into your original function, that 3, you're going to get 18 subtract 9, I do believe. So in other words, the point is 3, comma 9. Now you might look at your graph and think you know what it is, and probably you do, but we're still going to have to find or use the second derivative test. Now, let's also find the second derivative and see where there are any points of inflection. So I take y double prime. That will be equal to, well, remember now you're taking the second derivative, so it's just -2. If you set that equal to 0, you're going to get -2 is equal to 0. Now, when is that true? The answer is never. All right, there is no solution to that equation, so your conclusion would be no point of inflection. There is neither one. Okay, and if there's no point of inflection, then really you can leave out step 5. Well, we can do it anyway, but really, like, it's either going to be concave up forever or concave down forever, one or the other. Okay, now we also have to use the second derivative test to find out what that 3 is. Is that a maximum or is that a minimum? So you plug 3 into your second derivative, but now look at your second derivative. It's just -2. There is nowhere to put that 3. That is less than 0, so when the second derivative is less than 0, you know it's concave down, and therefore we have a max at 3, comma 9. There's a maximum there. Okay, what else do we need to do? Step 1, step 2, step 3. And that was step 4, by the way, right there. I didn't label it as step 4. You don't really need to label the steps as long as you do all your workings anyway. The only other thing that I'm going to do here now, I will include the table for concavity, but really there was no point of inflection to put into the table. I mean, I could put in the critical value of 3 and a point on either side. So we'll do that. But really what's going to happen is, by the way, you can plot your 3, 9 now as well. So what really should happen is, because there's no point of inflection, your table for the second derivative test should show no variation whatsoever. So we do something like this for step number 5. Now, ordinarily I'd put in my point of inflection here, but there is neither one, so I'll just put in 3. That's my x value, remember? Second derivative test, we're checking concavity now, remember? So second derivative into the second column. Pick a number a little bit less than 3, like a 2, a number a little bit bigger than 3, like a 4, and now you know what's going to happen here when you plug all of these in. You're going to get -2 anyway. -2. So concave down, concave down, concave down. It's concave down everywhere. Plot your 3 and 9. 3, 2, 4, 6, 8, 9 is right there. And there's the parabola you were probably expecting to get. And now we draw as smooth as we can. Smooth as I can with this old pen. And, oops, a little bit out there. But there's the graph. There's the first one. Example number 4 on page 14. Okay. Now the other one I'd like to have a look at with you is this one right here. Now I'm hoping I've got time in this 15-minute video to do this one. If not, I'll just make a part 2 video so you can watch both parts. Okay. So step number 1 is we get the x-intercept again. Okay, and I do that by setting my y equal to 0. So you're going to have 0 equals 2x to the power of 3 plus 3x squared minus 12x. Now that's a cubic equation. They're generally not that easy to solve, but this one happens to have a common factor of x. So if you take your x out in front, you'll have 2x squared plus 3x subtract 12. Okay, 2x squared plus 3x subtract 12. Now, I know what this part is going to tell me. That's going to tell me that x is equal to 0. So one of your x-intercepts is, well, 0, 0. All right, that's the origin. In fact, that's going to be your y-intercept as well, obviously, when you plug 0 in for x. This piece here now you have to solve. It would be nice if it factored, but I'm going to tell you right now, for this example, that one does not factor. So let me just tell you, if you would use the quadratic formula so I can save a little bit of time, here is the two solutions that you would have gotten, your two x-intercepts. One of them is approximately 1.81, so that would be an x-intercept of 1.81 comma 0. And the other root would be x equals negative 3.31. So that would give you an x-intercept of negative 3.31 and 0. Okay, so there's your three x-intercepts. Now, obviously, I took a few shortcuts there in hopes to save a little bit of time. Number 2, get your y-intercepts. And all you do there is you set your x equal to 0. So if you look at your function up there, look at your equation. Obviously, if you put in 0 everywhere, you're going to get y is equal to 2 times 0 cubed plus 3 times 0 squared minus 12 times 0. Wow, that doesn't look very nice. But anyway, you get y equals 0, so your y-intercept is also 0 comma 0. Okay, now let me see. I have to erase all of that. Note those points, by the way. All right, write down the coordinates of those points because you're going to be using them. You have to graph those. In fact, if you had a piece of graph paper already set up, and I have uploaded a sheet of graph paper, by the way, to D2L. If you go to D2L and check under topic number 6 on the left-hand side, all right, sketching the curve, you'll see that I've uploaded a PDF of some graph paper for you. Okay, so now step number 3. Step number 3. I wish there was some way I could, there probably is a way I can erase this really quickly. Step number 3, we need our critical values. And I've got about 3 minutes left, and I'm probably not going to be enough time. All right, so the critical values, that's your maxes and your mins. What you do is you take the first derivative, or well, y prime, or whatever you want to call it, or f prime of x, and it's going to be actually 6x squared, and then plus 6x, and subtract 12. That's your first derivative. Set that equal to 0. So plus 6x minus 12. And actually, you can take out a common factor there if you want. Common factor of 6 in front of x squared plus x minus 2. And now, fortunately, this does factor. All right, this does factor. So you're going to have x and x plus and minus plus 2 minus 1. Don't forget your equals 0. So the 6 now doesn't give you a solution. That's just a number. But this piece tells you x equals negative 2. And this piece here tells you that x equals positive 1. Again, you should plug those back into your original function to get your y coordinate. I'll tell you what they are. The y coordinate in this case is 20 when you plug it back in. And for the second one, when you plug your y back or x back in, you're going to get y is equal to negative 7. So negative 2, 20, and 1, negative 7. Now, they're maxes or they're mins. But remember, you don't know which yet. You're not sure. So that's where you have to do the second derivative test here now. The second derivative test. So this is step number 4. Now notice I haven't found the point of inflection yet, but I'll find that in my next step anyway. Because I have to get the second derivative here, you see. Second derivative is equal to 12x plus 6, and the 12 minus 12 vanishes. So y double prime. You plug in your two critical values. So if you put negative 2 in there, now you can see what you're going to get. You're going to get negative 24 plus 16. Well, that's negative 18. That's less than 0. And so that means it's a max because your graph is concave down. So now you know that the negative 220 is a maximum value. Plug it in as well into 1, just positive 1. And you're going to get 12 times 1 plus 6. Well, now you're going to get positive 18, so that's greater than 0. So that is a minimum value. That's a minimum. So what can be your conclusion from here? So now you know that negative 2 and 20, that is a maximum. And you also know that 1, negative 7, that, because of our second derivative test, that one is a minimum. Now I'm almost out of time. I still haven't done the point of inflection yet. I have to find that, and I also have to do up my table afterwards for concavity. So I'll end this video here and call this part 1. And so I'll just make up another video now, part 2, and so you can watch part 2 after this part, okay? So I'll see you in just a moment.